Welcome, everyone, to Deep Dive Ortho, where we cut through the noise to bring you the crucial insights shaping healthcare. Today, we're getting stuck into an incredibly vital topic, one that's evolving really rapidly: the privacy of patient data in healthcare. Especially, as artificial intelligence continues its relentless advance.
Indeed.
It's a conversation every healthcare professional really needs to be having right now, wouldn't you say? Because the landscape of data protection, well, is changing faster than many realize. It presents immense opportunities and some pretty significant risks, too.
Absolutely. The pace of change is quite remarkable.
At its heart, the challenge seems clear enough.
Yeah.
How do we effectively harness the immense, truly transformative potential of data-driven medical research? Think breakthroughs in diagnostics, personalized medicine, predictive analytics, all that amazing stuff. While at the same time, absolutely safeguarding patient confidentiality, that non-negotiable necessity.
That's the crux of it, precisely. That tension.
And this balance, it feels like it's becoming exponentially more complex with the rise of sophisticated AI. Especially these large language models, right? They can process, infer, even generate information in ways we couldn't have imagined just a few years back.
That's right. Their capabilities introduce whole new dimensions to the privacy challenge.
So our mission today is to explore this intricate interplay. We want to understand where we've been, where we are now, and crucially, where we must go to ensure ethical, effective healthcare innovation. And to guide us through these intricate layers, we're joined by a true expert in this field. Professor, it's a pleasure to have you with us.
Thank you. It's a real pleasure to be here and contribute to such a crucial discussion.
Brilliant. Professor, let's start right at the beginning with the raw material itself. Electronic health records, EHRs, they're often described as a gold mine for medical research. Could you elaborate a bit on why they're considered so incredibly valuable for advancing healthcare?
Indeed, yes. The metaphor of a gold mine is, I think, remarkably apt. EHRs are, well, they're a treasure trove of information, aren't they?
Yeah.
They capture the entirety of a patient's journey within the healthcare system, often over many, many years.
Right. Longitudinal data.
Exactly. They contain this wealth of longitudinal data, detailed diagnoses, treatment plans, medication histories, lab results, imaging reports, patient outcomes. It's incredibly rich. And this rich, real-world data is absolutely invaluable for a whole myriad of research purposes that, frankly, couldn't exist without it.
Such as?
Well, consider epidemiological studies, for instance. Tracking the prevalence and patterns of diseases across vast populations, identifying trends, risk factors, that relies heavily on EHR data. Or disease modeling, where we try to predict the progression and impact of various conditions. That helps us anticipate needs, allocate resources more effectively. And of course, EHRs are the very foundation for developing and validating new AI models. Models designed to improve diagnostics, streamline treatments, enhance operational efficiencies, even power predictive analytics in clinical settings. Imagine an AI trained on millions of EHR entries to flag the early signs of sepsis, maybe, or to identify which patients are most at risk of hospital readmission.
That's powerful stuff.
It is. Without this granular real-world data, much of the advanced research and clinical AI development we're seeing today simply wouldn't be possible. The sheer volume and depth of information within EHRs offer an unparalleled view into patient health. They really are indispensable for medical innovation.
Okay, so it sounds like the essential raw material for unlocking that next generation of medical breakthroughs. But of course, this raw material, as you said, often contains highly sensitive personal details, which brings us neatly to protected health information, or PHI. Could you perhaps define what PHI actually encompasses? And importantly, what are the legal frameworks governing its use, particularly for research?
Yes, you've hit on the core dilemma there. That tension between data utility and patient privacy. Protected health information, PHI, it refers to any health information that can be linked, or potentially could be linked, back to an individual.
So not just the obvious things like a name.
Oh, definitely not.
Yeah.
It includes their health history, treatments received, lab results, but also demographic data if combining it could potentially identify them. Essentially anything in a medical record that points back to a specific person. It's broader than many people initially think.
Right.
And to govern this incredibly sensitive data, various legal frameworks exist globally. They reflect the sort of shared understanding of its importance. In the United States, you've got the Health Insurance Portability and Accountability Act, AIPay, which most people have heard of. Across the European Union, the General Data Protection Regulation, GDPR, sets a very comprehensive standard for data privacy, including health data. And here in Canada, for example, there's FIAP, the Personal Health Information Protection Act. These regulations are all designed to ensure patient privacy and the secure, ethical handling of health data. They essentially establish the rules of engagement for researchers and healthcare providers alike.
Okay. So if we take IPA as a key example, given its influence over the years, how does it actually allow data to be used for research while protecting identity? What are the mechanisms?
Right. IPA outlines two main methods for de-identification. This is the process that allows data to be used for research without theoretically directly identifying individuals. First is the safe harbor method. This one is quite prescriptive, quite well known in the field, actually. It mandates the explicit removal of 18 specific types of identifiable information.
18.
Yes, and it's a comprehensive list designed to strip away common identifiers. It's not just about names. For instance, it requires removing all geographic subdivisions smaller than a state. So, street addresses, cities, even postcodes.
Why postcodes? They seem quite broad.
Well, even a seemingly innocent combination, say a postcode, age, and perhaps a rare medical condition, can sometimes be enough to pinpoint an individual in certain contexts. So it aims to remove that risk. It also covers all elements of dates directly related to an individual, admission dates, discharge dates, birth dates, though the year itself can sometimes remain.
Oh, okay.
The idea is that specific dates of service could potentially be cross-referenced with other publicly available information. Then there are the direct contact details.
Yeah.
Telephone numbers, fax numbers, email addresses, and the really unique identifiers like social security numbers, medical record numbers, account numbers. Those are crucial.
Yeah.
It also includes more modern digital traces, vehicle identifiers, device serial numbers, URLs, IP addresses, biometric identifiers, two fingerprints, retinal scans, full-face photos, any comparable images. Health plan beneficiary numbers are on the list. And importantly, it includes a sort of catch-all. Any other unique identifying number, characteristic, or code.
That sounds quite thorough.
It aims to be. The underlying idea of safe harbor is to strip away enough information so that the data can no longer be reasonably linked to an individual, tackling the common ways re-identification might happen, making it statistically improbable.
Okay, that's safe harbor. What's the second method?
The second method under IPATA is the expert determination method. This approach offers a bit more flexibility. It allows for de-identification through statistical methods. The key difference here is that a person with appropriate knowledge and experience, specifically in statistical and scientific principles, must formally certify that there's a very small risk, and that's the precise legal term.
Very small.
Yes, a very small risk that the information could be used, either alone or in combination with other reasonably available information, to identify the individual. This expert has to thoroughly document the specific methods they used for de-identification and the results of their analysis. They need to provide a robust justification for their determination.
And that documentation has to be kept.
Absolutely. Meticulously kept for at least 6 years, along with the certification itself. This method places a higher reliance on statistical rigor and the informed judgment of a knowledgeable expert rather than just a fixed list of removals. It's less about removing specific fields and more about achieving statistical confidence in the anonymity of the data.
So, Professor, those are the legal and theoretical underpinnings, the frameworks that have guided practice for decades now. But as anyone working in a hospital or clinic knows, theory meets reality, doesn't it? The practicalities can be vastly different. I can only imagine applying these principles to the sheer volume of real-world patient data is a massive undertaking. What are the key practical challenges?
Oh, the practical challenges are indeed significant, and they often boil down to resources, scalability, and precision. Historically, and actually still quite commonly, manual de-identification of clinical free text, the unstructured notes written by doctors and nurses, is extraordinarily time-consuming.
I bet.
And consequently, very, very costly. Imagine a team of highly trained individuals meticulously reading through thousands, maybe millions, of patient notes, identifying and redacting every single piece of PHI.
It sounds laborious.
It is, and research has put some quite stark figures on this cost. Studies have shown the median cost per single PHI annotation can range from maybe $1.71 for an initial annotation by one person, all the way up to a staggering $377 for annotations that require input from, say, a fourth annotator to resolve disagreements or complex cases.
$377 for one piece of information.
That median figure, yes, in complex scenarios. It's genuinely staggering when you think about the volume of PHI in clinical notes. It really puts the scale of the challenge into perspective. We're not just talking about removing a name here and there. It's an army of skilled people making nuanced judgments over vast amounts of text.
So that high cost really underlines the need for automated solutions then.
Absolutely. It underscores the absolute necessity for automation to make large-scale de-identification feasible, economically viable for healthcare organizations wanting to use their data for research or AI. Manual methods just don't scale.
So how does automation approach this? You mentioned natural language processing, NLP.
Yes, in the world of NLP, the field focused on getting computers to understand human language de-identification is commonly modeled as a named entity recognition task, NER for short.
Named entity recognition. Okay.
Now, for listeners maybe not deep into computational linguistics, NER is essentially about identifying and classifying predefined categories of named entities in text. In our context, these entities are the different types of PHI. So the system is trained to recognize specific categories like names, dates, locations, medical record numbers within that unstructured clinical text, like progress notes or discharge summaries.
How does that process typically work?
It usually involves several stages. First, there's pre-processing. Think of this as tidying up the raw text before the main analysis. This involves tasks like splitting sentences and then tokenization, which is simply breaking the text down into individual words or meaningful units. Tokens like patient, diagnosis, or even punctuation.
Right.
Sometimes we look at anagram sequences of N-words like blood pressure as a two-word sequence, helping the system understand common phrases. We also do part-of-speech tagging, identifying nouns, verbs, adjectives, and so on.
Do standard tools work well for this? Clinical language is quite specific.
That's a very good point. Often, general domain NLP tools like Stanford Core NLP or OpenNLP are used for pre-processing. They're widely available. However, it's been found in about 14 studies, actually, that specialized tokenization modules developed specifically for clinical text can actually improve performance. They can boost the F1 scores by 2 to 3 percentage points.
So tailoring it helps.
It does. It suggests that while general tools are a decent start, the unique jargon, abbreviations, and grammatical quirks of clinical language really benefit from bespoke refinement. After pre-processing, you have the core task, PHI recognition and classification. This is where the system identifies and labels the sensitive bits, marking them for removal or redaction. And finally, there's often an optional post-processing stage. This might involve applying further rules to catch anything missed, or perhaps correcting misclassifications based on context.
That makes perfect sense. The devil really is in the details with clinical language, isn't it? So we've established EHRs are a gold mine, but getting that value without compromising privacy has historically been this huge, costly challenge. It sounds like a problem ripe for technological solutions. Can you tell us how the methods for de-identification have actually evolved, especially that shift from isolated proprietary efforts towards a more collaborative public approach?
Absolutely. Historically, say, before around 2010, most de-identification systems were developed and evaluated pretty much in isolation on proprietary data sets held by individual institutions. This naturally limited collaboration and made it very difficult for researchers to reliably compare how well their systems performed against others. So it's quite a fragmented landscape.
Right, everyone working in their own silo.
Precisely. But a major turning point came with the introduction of shared tasks, particularly the 2014 I2B2U Health Shared Task. The I2B2 challenges informatics for integrating biology in the bedside. They've been hugely instrumental in healthcare NLP. This specific 2014 event and the subsequent release of its data resources in 2015 profoundly influenced the field. It created a common ground, a standard benchmark.
A level playing field.
Exactly. And it led to a dominance of publicly available corpora, which enabled researchers globally to test and compare their methods on the very same data. This fostered a real explosion of innovation and collaboration that just wasn't possible before. The 2014 I2B2U Health Corpus is by far the most frequently used in clinical de-identification research. We've seen it in 36 studies we looked at. Following that, the older 2006 I2B2 corpus has been used in about 18 studies, and the 2016 CEGS NGRID corpus in 10 studies. These public data sets have become foundational.
Can you give us a flavor of what these key data sets are like? What makes them different?
Yes, understanding their characteristics is important because it highlights the evolving challenges. The 2006 I2B2 corpus, for instance, had 889 discharge summaries from Partners Healthcare. They were annotated with 8 PHI categories, the 6 IPA ones, plus the organizers added doctor and hospital names, deeming those critical. Multiple annotators labeled them to ensure accuracy.
Okay. And the 2014 one?
The 2014 I2B2U Health Corpus was a significant step up in complexity. It had 1,304 longitudinal records from 296 patients, also from Partners Healthcare. Its annotation scheme built on HIPAA but expanded it significantly. It included annotating all parts of dates, including years, more granular location details like states and countries, hospital names, doctor names, nurse names, even patient professions, things that could indirectly identify people.
More subtle identifier.
Exactly. And the agreement between the annotators for this corpus was impressively high, a micro F1 score of 0.895 for entity-level agreement. That signals excellent consistency and reliability in the labeling, which is vital for training robust models.
And the third one, the 2016 CGN Gradit.
Right, that one consisted of 1,000 psychiatric intake records, again from partners. This data set presented a different set of challenges, reflecting real-world clinical notes perhaps even more closely. These records often contained a lot more spelling and punctuation errors, a common headache, as you know, in free text clinical data.
Oh, yes.
And importantly, they included a considerably wider range of unique identifiers, things like places the patient had lived, specific jobs they held, hobbies, details of traumatic events, even pet names.
Pet names, really?
Yes. Reflecting the more narrative, sometimes informal nature of psychiatric notes, this broader, more informal scope led to slightly lower inter-annotator agreement, a micro F1 of 0.851. Still good, but reflecting that increased ambiguity. And a critical detail for all three of these foundational corpora. The PHI wasn't just deleted. It was replaced with realistic surrogates, fake but plausible data.
Why do that?
It maintains the clinical context and the narrative flow of the records. This allows researchers to develop and test models that might need the full story while still removing the actual patient identifiers. It's crucial for maintaining data utility. This meticulous curation of public datasets has been absolutely fundamental.
It's clear these public datasets really catalyze development. So, with these tools available, can you break down the main types of methods that emerged, starting with the earlier approaches before deep learning really took hold?
Of course. Early de-identification methods broadly fall into two main camps: rule-based systems and traditional machine learning-based systems, though often modern systems are actually hybrids, combining elements of both.
Okay, let's start with rule-based.
Right. Rule-based systems. About a third of the studies we reviewed, 31 to be precise, applied at least one rule-based tagger. Interestingly, though, only 6 studies relied entirely on rules, which is a notable shift from the pre-2010 era, where more than half were purely rule-based.
So they became more of a component than the whole solution.
Exactly. They excel at detecting the more formulaic categories of PHI. We're talking things like contact information, phone numbers, email addresses. Those were detected by rule-based methods in 22 studies because they follow very predictable patterns. Person names were targeted in 19 studies, dates in 18, geographical locations also in 18. They primarily work using regular expressions, the sequences of characters defining a search pattern.
Radix.
Yes, and predefined heuristics, essentially rules of thumb, or by leveraging structured fields from the EHR itself, like a date of birth field providing a direct clue. Their strengths lies in high precision for those well-defined patterns, and they're interpretable. You can see exactly why a rule fired.
Okay, and the other camp, traditional machine learning.
Yes, traditional ML-based systems saw a significant increase in use after 2010. Conditional random fields, CRFs, became the most widely applied model in this category. They featured in 20 ML-based and 18 hybrid systems.
CRFs, can you briefly explain what they do?
Sure. A CRF is a type of statistical modeling method. It's particularly good at pattern recognition and sequential data like sentences in a clinical note. It looks at the context around a word. The core idea behind these traditional ML systems is their reliance on what we call handcrafted features. Think of it like a detective building a profile. Researchers would painstakingly extract specific clues or features from the training data. These features fall into categories: lexical features, about the words themselves, maybe character patterns; dictionary features, does a word match a list of known names or places; orthographic patterns, capitalization, numbers; and word representation features, using models like Word2Vec that capture word meaning and context numerically.
Which features were most useful?
Well, lexical features and word representation features were the most frequently extracted, used in 29 and 27 studies respectively. That shows their power in capturing general language patterns. Dictionary features were also very popular, in 23 studies. And a key insight here is that integrating structured EHR data information from the non-text parts of the record can significantly boost recall, especially for patient names.
How so?
Well, if you know a name appears in the structured patient name field elsewhere in that same record, it provides a strong hint for the NER system when it encounters that name in the free text notes. It gives extra context.
Right, cross-referencing.
Exactly. These traditional ML approaches, while powerful, were heavily dependent on the quality and comprehensiveness of those manually engineered features. That took a lot of expert effort.
So we have these different methodologies, all meticulously designed to protect patient privacy. But how reliable are they actually in practice? What do we know about their performance? Can they truly de-identify data safely and effectively for real-world use?
That's a crucial question, and it highlights one of the ongoing challenges. There isn't really a single, universally adopted, industry-wide standard for evaluating these systems. However, a pragmatic rule of thumb has sort of emerged in the research community. It suggests that an F1 score of 95% is generally considered indicative of a system's ability to reliably de-identify data for safe distribution.
The F1 score, can you remind us what that measures?
Yes, the F1 score is essentially a balanced measure. It combines two things. Precision, how many of the items the system flagged as PHI are actually PHI. And recall how many of the actual PHI instances did the system successfully find. So a 95% F1 score signals a high degree of confidence, a good balance between not missing sensitive data, high recall, and not redacting too much non-sensitive data, high precision.
Okay, 95% is the target. Do systems achieve that?
Well, many of the best performing systems do achieve this token level F1 score. However, it's really important to acknowledge that perfect 100% de-identification remains elusive. We don't yet have a system that can guarantee absolute perfection in all real-world scenarios. There's always likely to be a minute residual risk.
But have there been examples of systems getting very close, especially on recall? Minimizing what gets missed?
Yes, there have been some impressive results on recall. For instance, one group, Abdallah and colleagues, developed a method using word embeddings that achieved a remarkable 100% recall. However, this came at the cost of readability and potentially data utility, because it was quite aggressive in its replacements. Others, like Ahmed et al. On MIMEC3 data using a GRU network, and Zhu et al. On selected reports, also reported reaching 100% recall using different embedding techniques. So these examples show the potential for a very high recall, ensuring systems are generally very good at finding what is PHI.
But is that the whole picture? Does high overall F1 mean it works well for all types of PHI?
That's where it gets more nuanced and frankly highlights some vulnerabilities. Even with a high overall F1 score, certain categories like contact information, identifiers, location, and name are not consistently recognized with equally high F1 scores.
So some types of information are harder to catch.
Exactly. For example, in that 2016 CES NGRADI corpus, the psychiatric notes one, remember, even sophisticated RNN-based systems often struggle to get location and name categories above that 95% F1 target. This is often because names and locations can be highly variable, context-dependent, and don't always follow rigid patterns. Think of nicknames or vague location descriptions. The identifier category in particular suffered from really scarce training data in that corpus, only 38 examples in the training set, 21 in the test set. This highlights a significant issue. If a category has very few examples for the model to learn from, even advanced machine learning will struggle to identify it accurately.
So the overall score can hide weaknesses in specific areas.
Precisely. Relying solely on overall metrics, like the micro F1 score, without looking at the detailed category-level performance, can create a false sense of security. It might obscure poorer performance on these less frequent but equally critical PHI categories. It's like the weakest link in the chain, leaving patients potentially vulnerable through those less reliably anonymized data points.
That's a really important point. What about the other side of the coin, removing too much? You mentioned overscrubbing.
Yes, overscrubbing. That's a concern, particularly for researchers and AI developers, that the de-identification process might remove too much useful information, inadvertently impairing the data's utility for its intended purpose. If you remove too much context, the data becomes less valuable or even useless.
Has research looked into this trade-off?
Yes. Thankfully, studies have started to address this balance. For example, Dellinger et al. Found that de-identification had no statistically significant impact on medication detection performance in clinical notes. In fact, the F1 score was even slightly higher on the de-identified notes in their study.
Interesting.
And another study by Bowie et al. Showed that readability wasn't significantly affected whether PHI was replaced with a single generic marker or more specific category markers. Expert reviewers largely agreed. This suggests that in many cases, if done carefully, de-identification doesn't necessarily ruin the data's usability.
But it's not always straightforward.
No. Ahmed et al. Made a vital point. When analyzing data utility after de-identification, you absolutely have to consider both precision and recall. A system that overscrubs might achieve perfect recall by removing almost everything sensitive, but it would render the data useless because its precision would be terrible. It removes too much valuable clinical context and nuance along the way.
Right. You might redact the word diabetes just in case it's someone's unusual name.
Exactly. Clearly absurd, but it illustrates the point. Finding that balance between comprehensive PHI removal and retaining sufficient clinical utility is paramount. We need systems smart enough to know what to remove, and just as importantly, what to leave behind for the research or AI task.
That's a comprehensive look at traditional methods and their performance. It sounds like while we've made huge strides, especially with public data sets pushing things forward, achieving truly robust, consistent de-identification across all PHI categories is still, well, a work in progress. Now let's bring ourselves right up to the present day. The AI era, deep learning, those massive large language models, they've arrived. How has this new landscape, this potential game changer, fundamentally impacted how we approach de-identification?
The arrival of deep learning, and more recently large language models, truly marked a new chapter in NLP, and definitely in de-identification too. After that 2014 I2B2U health corpus came out, we saw a rapid adoption of more sophisticated neural network architectures. Recurrent neural networks, RNNs, and then later, transformer architectures became the go-to methods.
Transformers like BERT.
Exactly. You hear terms like BERT, CyBERT, BioBERT. These are all transformer models, specifically adapted or trained for biomedical text. The bidirectional LSTM, a type of RNN often combined with a conditional random field, or CRF inference layer on top, became a particularly popular and effective architecture for de-identification during this period. It showed significant improvements over older methods because it could better understand context and long-range dependencies in the text.
But what about the really big LLMs like GPT 3.5 or GPT 4? How have they fared when applied directly to this task?
Well, the initial findings for using these general-purpose LLMs directly for de-identification have been quite revealing, actually. A recent study, Kugia et al. In 2024, looked at a related task, zero-shot temporal relation extraction in biomedical text. Zero-shot means the LLM got no specific training examples, just instructions. And they found models like GPT 3.5, Mixtral, Llama 2, Gemma, PMC Llama actually performed worse than specialized models that had been fine-tuned for the task. They particularly struggled with things like temporal consistency, ensuring uniqueness and logical flow in time relationships between events. Consistency doesn't guarantee accuracy, though, right? Spot on. Their analysis revealed a crucial point. Even when these LMs achieved temporal consistency, their predictions could still be inaccurate. It really underscores that while LLMs are incredibly powerful, just applying them directly off the shelf to sensitive, nuanced tasks like de-identification isn't always reliable, particularly in the biomedical domain where precision and safety are absolutely paramount. They can hallucinate or misinterpret context in ways that fine-tuned specialized models tend not to.
That's a really intriguing finding. It suggests that despite their power, a sort of plug-and-play approach with general LLMs isn't the silver bullet some might have hoped for in this highly sensitive clinical context. It echoes that idea that specialist tools often beat generalists for specific high-stakes jobs. So if direct LLM use is struggling, what is this newer paradigm you mentioned, the LLM in the loop methodology? That sounds like a cleverer way to leverage their power without the direct risks.
Precisely. The LLM in the loop methodology is designed exactly to address the limitations of using large general-purpose LLMs directly, especially in sensitive areas like healthcare, while still harnessing their incredible capabilities. So instead of treating the LLM as the final, standalone de-identification tool, this innovative approach leverages their power during the development process of expert small AI models.
So the LLM helps build the tool, but isn't the tool itself.
Exactly. Think of it as using LLMs as highly sophisticated, incredibly efficient assistants to build more precise, efficient, and secure specialized tools.
How does that work in practice then? What does the LLM actually do in the loop?
Well, LLMs are used selectively at various stages of developing these smaller, expert models. For example, they can be brilliant for synthetic data generation. This means they can create large volumes of realistic-looking, but entirely non-sensitive data that mimics the patterns and nuances of real clinical notes.
So you get more training data without using real patient data.
Precisely. This synthetic data can then be used to rigorously train the smaller, expert models without ever compromising actual patient privacy. It allows for much larger, more diverse training sets than could ever be manually annotated. They also assist in rigorous evaluation, providing a rapid, scalable way to assess the performance and identify weaknesses in the developing expert models before they get deployed. And furthermore, LLMs can be used for agent orchestration, effectively managing and refining the workflow of data labeling, quality control, model training, making the whole development pipeline much more efficient.
And the key difference is the final model doesn't need the LLM anymore.
That's the critical distinction. These expert small AI models, once developed, operate independently. They don't rely on transmitting sensitive patient data to external cloud-based LLM APIs for the actual live de-identification. That entirely overcomes the significant privacy risks associated with that kind of external data transfer. The sensitive data stays within the secure environment.
And the benefit? How do these expert small models perform?
The significant benefit is profound. These expert small models consistently outperform general-purpose LLMs like GPT-4o when it comes to the actual de-identification task. This translates directly to superior performance, higher reliability, and crucially enhanced safety, which is absolutely non-negotiable when dealing with patient data.
Have these been tested widely?
Yes, we've seen truly impressive multilingual success. They've been developed and rigorously tested across 8 languages: English, German, Italian, French, Romanian, Turkish, Spanish, and Arabic. Across these diverse languages, they've achieved F1 microscores averaging between 0.953 and 0.978.
That's getting close to that 95% rule of thumb, or even exceeding it.
Indeed, these results establish them as some of the most accurate and reliable healthcare anonymization solutions available today, showing their broad applicability. For English specifically, models developed using this approach, augmented with synthetic data and LLM-assisted labeling, achieved a macro average F1 score of 0.931 on that I2B2 2014 test set. That actually sets a new state-of-the-art for this widely recognized benchmark.
A new state of the art.
Yes. It's a clear demonstration that specialized, carefully developed models, even if they're small compared to the giant LLMs, can deliver precision and safety that general models, used out of the box, simply cannot match for this task. It really highlights the power of targeted, domain-specific AI.
That's a truly stark difference in performance, Professor, especially comparing that 0.931 F1 score to what you mentioned earlier for direct LLM use. It really hammers home the importance of domain-specific solutions in healthcare. But to really underline this point, could you walk us through some of the specific types of errors or failures you actually see when general-purpose LLMs like GPT-4o are used directly for de-identification? What does that lower F1 score you mentioned, as low as 0.548, actually look like in practice? What goes wrong?
It's crucial to understand, yes, because a low F1 score isn't just an abstract number. It represents real failures in protecting sensitive patient information, or conversely, mangling useful clinical data. When GPT-4o was used directly for de-identification in studies, it struggled significantly with certain critical PHI categories. We saw particularly poor performance for things like ID and identifier numbers, location, other those more nuanced or non-standard location descriptions, organization like specific hospital or clinic names, email, AX, and device identifiers. This poor performance on key categories resulted in that macro average F1 score dropping as low as 0.548 in some cases, which is simply nowhere near acceptable for clinical use.
What kinds of mistakes lead to those low scores?
Several types of issues were observed. For instance, the model sometimes failed to identify patient and doctor names when they appeared, say, in the middle of the text rather than at the beginning or end, which happens all the time in clinical notes, doesn't it?
Absolutely. Names can pop up anywhere.
Exactly. We also saw partial labeling of hospital names. So the model might identify the word hospital, but completely miss the specific name attached to it, like St. Elsewhere's Hospital. That affects both precision and recall. Occasionally, the model would include extra adjacent words within the identified label, leading to incorrect annotations. It might grab a conjunction or a verb and include it as part of a name, for example.
Sloppy boundaries.
Sort of, yes. And even when explicitly prompted with the exact list of labels to use, GPT-4 sometimes incorrectly added labels that weren't meant to be included. It might label a random word as time or age when it clearly wasn't. So, in essence, these general-purpose LLMs can confuse labels, miss them entirely, especially in unusual contexts, or even introduce their own hallucinated labels. All these issues contribute to those significantly lower scores when they're applied directly to this intricate, high-stakes task. It just reinforces the fact that general intelligence doesn't automatically equate to domain-specific accuracy and safety, particularly when patient privacy is paramount.
That's a powerful and, frankly, quite concerning illustration of the shortcomings of applying general LLMs directly to sensitive data like this. It also leads us directly into a really critical discussion about the limitations of our current privacy frameworks themselves. Professor, you've made a rather provocative yet deeply concerning claim earlier that idempotay, the very bedrock of patient privacy in the U.S. for so long, is becoming increasingly obsolete in today's world. You even called relying on it a dangerous illusion. Can you perhaps unravel for us what you mean by that? Why might a law designed to protect us actually be putting us at greater risk now?
It's a crucial point, and one I believe healthcare professionals, researchers, and regulators urgently need to grapple with. While HIPAA was absolutely groundbreaking when it was enacted back in 1996, well, the digital world has transformed almost unrecognizably since then. We now operate under what I genuinely believe is a dangerous solution. The assumption that simply removing those 18 specific identifiers via the safe harbor method truly, effectively anonymizes patient data in today's hyper-connected world. This assumption is, frankly, deeply outdated and potentially puts millions of patients at risk.
Why is this so much riskier now?
A truly alarming finding from a 2018 paper in Nature really drives this home. Research has demonstrated that an astonishing 99.8% of patients from a supposedly de-identified dataset could actually be re-identified using just 15 demographic attributes.
99.8% with just 15 data points.
Yes. Think about that. A combination of things like postcode, date of birth, and sex, often considered safely de-identified under safe harbor, can, in many cases, be enough to uniquely single someone out in large datasets. This means that even when the safe harbor rules are meticulously applied, the resulting data often isn't nearly as anonymous as we might assume, or as it perhaps once was. The sheer volume of other data available today, from public records, social media profiles, consumer marketing databases, voter rolls, makes re-identification attacks far, far easier than they were nearly 3 decades ago when HIPAA was conceived. The anonymity is often incredibly fragile.
And that fragility leads to a legal problem, you mentioned.
Exactly. This leads to a critical legal loophole with really profound consequences for patients. Once data is formally de-identified according to HIPAA standards, it is legally no longer considered protected health information, PHI.
Right, it's outside HIPAA's protection then.
Precisely. And that means it loses all the related privacy protections afforded by HIPAA. So as a result, if this de-identified data is subsequently re-identified by a third party that is not a HIPAA-defined covered entity, so not the original hospital, doctor, or health plan, but maybe a data broker, an insurance company looking for underwriting information, an employer.
Or someone malicious.
Or someone malicious, yes. And if that re-identified data is then used for nefarious purposes, identity theft, targeted advertising based on sensitive health conditions, healthcare fraud, employment discrimination, the patient has absolutely no legal protection or recourse under HIPAA itself. It's a significant vulnerability.
How does that compare internationally? You mentioned GDPR earlier.
It's a stark contrast. The European Union's stance under GDPR, for example, is quite different. GDPR regulations essentially mandate that for data to be considered truly anonymous, and thus outside the scope of GDPR, the anonymization must be effectively irreversible. If de-identified data can be re-identified, even by a third party, it generally still falls under data protection rules. This fundamental difference in legal philosophy creates a significant gap in protection for patients under the current U.S. framework, a gap that's only widening as data analytics and AI become more powerful.
So there's the re-identification risk and the legal loophole. Are there other limitations of this traditional de-identification approach, particularly for AI development?
Yes. Beyond those critical issues, there are significant practical limitations for clinical AI development itself. Many important types of data that are absolutely crucial for building robust, comprehensive, and cutting-edge AI models simply cannot be effectively de-identified using traditional methods. Or the process is far too risky, too costly, or too time-consuming to be practical.
What kinds of data are we talking about?
This includes incredibly sensitive and information-rich data, like certain types of genomic data, high-resolution retinal, and iris images, which are effectively unique, biometric identifiers, other kinds of medical imaging and video data, like surgical footage perhaps, and also critically, insights derived from social determinants of health details about a patient's living conditions, socioeconomic status, environmental exposures. These factors are hugely important for understanding health outcomes and building equitable AI.
But hard to anonymize without losing the meaning.
Exactly. These rich data sources are invaluable for developing truly powerful AI models that could diagnose genetic predispositions, predict disease risk based on environment, identify social risk factors. But traditional de-identification methods really struggle to handle them without either destroying the critical utility or posing an unacceptably high re-identification risk. It's a major bottleneck for more advanced, holistic AI in healthcare.
And can the de-identification process itself actually harm the AI models?
Yes, absolutely. The process itself can inadvertently impair AI model performance. Imagine an algorithm designed to predict patient outcomes based on the precise timing of various clinical events, say. the sequence of drug administration, and vital sign changes after surgery. Now, if, as part of de-identification, dates are randomly modified, shifted by a certain amount, or generalized, like changing a specific date to just the month or year to obscure exact service times, well, that algorithm's ability to learn from and predict based on that time-sensitive data would be severely compromised.
It's learning from distorted information.
Precisely. It would be learning from noisy or inaccurate temporal patterns. It's a classic case of rendering the data not fit for purpose for that specific task. For AI models to be truly robust, reliable, and importantly, to meet the stringent regulatory requirements for validation, like those from the FDA or EMA, they absolutely need to be developed and evaluated on unadulterated, real-world patient data. Traditional de-identification, by altering or removing potentially crucial information, can introduce biases, noise, or distortions that prevent us from fully realizing the immense potential of AI in clinical settings. The integrity of the data is paramount for the integrity and trustworthiness of the AI built upon it.
That's a really powerful argument for a fundamental rethink, Professor. If traditional de-identification is no longer sufficient, if it's potentially risky and can even hinder the very AI innovation it's supposed to enable safely, what are the promising new avenues? Let's turn our attention now to what you've termed privacy-enhancing technologies, or PTs. How do these offer a more robust solution, one that promises perhaps both greater privacy and greater utility?
This is indeed where the innovation truly lies, and where I strongly believe the future of health data analytics and AI is headed. Privacy-enhancing technologies, PETs, represent a really transformative shift. They offer far more robust patient data protection, without suffering from the significant drawbacks of traditional de-identification drawbacks like the high cost, the residual risk of re-identification, or that critical loss of data utility we just discussed. The key difference is that PETs are often about protecting the data while it's being used, rather than just trying to strip identifiers out beforehand. One of the leading PETs in this space, and arguably one of the most promising for healthcare, is confidential computing.
Confidential computing, how does that work?
Confidential computing platforms provide complete data protection through a combination of end-to-end encryption and what are known as secure computing enclaves. Now, for our listeners, you can think of a secure computing enclave as a highly protected, isolated environment within the computer's processor itself, like a locked black box inside the chip. In essence, data remains encrypted not just when it's stored, data at rest, or when it's being sent across a network, data in transit, which are standard practice. But crucially, it remains encrypted even while it's being actively processed inside the computer's memory, data in use. This technical capability fundamentally changes the game. It entirely eliminates the need to transfer sensitive data to third parties, like cloud providers or AI developers, in an unencrypted plaintext form. The computation happens inside that protected enclave, which even the cloud provider or a malicious actor with server access cannot peer into.
So the data stays protected even during analysis.
Exactly. For healthcare organizations, the benefits are immense. They can keep their sensitive patient data entirely within their own HIPAA-compliant protected data environment, but with this added hardware-enforced layer of security during the entire computing life cycle. This allows them to safely leverage their valuable data assets for both internal research and for external collaborations, including potentially lucrative industry-funded projects, creating new opportunities without ever losing control or exposing plaintext data.
What about the AI developers?
It also inherently protects the intellectual property of the AI developers. Their proprietary algorithms can run securely on the encrypted data within the enclave without exposing the underlying code or model weights to the data owner. It's a two-way street of protection. And critically, AI developers get to work directly with unadulterated, real-world patient data inside this secure environment, which, as we discussed, is absolutely paramount for achieving more reliable model performance and meeting those stringent regulatory requirements for model validation. It enables trust through verifiable technical security, not just through the often imperfect process of de-identification.
That sounds incredibly promising. What other PTs are important in this space? You mentioned federated learning earlier.
Yes, federated learning is another PT that's gaining significant traction. Its main strength is that it addresses a core privacy concern by ensuring the raw data never leaves the data holder's protected environment. So instead of centralizing all the sensitive patient data in one place, which creates a very attractive target for cyber attacks, the machine learning models are sent out to the individual data sources, say to different hospitals or research centers participating in a study.
The model travels, not the data.
Exactly. The models are then trained locally on each institution's private data set, and only the updated model parameters or weights, the learning adjustments from that local training, are aggregated back to a central server to create an improved global model. The raw, sensitive patient data never leaves its original secure location.
Are there downsides to federated learning?
While it's a significant step forward for privacy, federated learning platforms, on their own, do have some potential vulnerabilities. They can be susceptible to certain types of privacy attacks, where clever adversaries might try to infer sensitive information from the shared model updates or weights themselves. It's not impossible. Furthermore, standard federated training doesn't inherently protect the intellectual property of the AI model developers as their model updates are being shared, albeit in aggregated form.
So are there solutions to those issues?
Yes, a powerful solution is rapidly emerging, combining federated learning with confidential computing. This creates what's known as secure federated learning. This hybrid approach addresses many of the existing challenges, offering a truly robust framework for both privacy and intellectual property protection. It allows secure collaboration on training models across institutions without exposing either the raw data or the core algorithms.
Interesting. Any other major pitfalls we should know about?
One other significant one is secure multi-party computation, or SMC. SMC is another advanced PE that uses sophisticated cryptographic techniques to protect both the data and the algorithms during computation. It allows multiple parties to jointly compute a function over their private inputs without ever revealing those inputs to each other. So you could run a complex statistical analysis or train a machine learning model across different data sets held by, say, a pharmaceutical company, a hospital, and a research institution, without any single party seeing the raw data from the others.
How does that work? It sounds almost like magic.
It's complex cryptography. The key is that only the final result of the computation is revealed, and only to the authorized parties. The inputs remain completely private throughout. While incredibly powerful for privacy, SMC often requires higher levels of collaboration and more coordinated real-time interactions between the data holders and algorithm developers. Setting up these intricate protocols and ensuring technical integration across disparate systems can be quite challenging, especially in complex, often resource-constrained healthcare environments. Each of these P-types, confidential computing, federated learning, especially secure federated learning, and SMC offers distinct advantages. Their strategic adoption, often in combination, is really key to unlocking the future of ethical and effective AI in healthcare.
It's clear that these privacy-enhancing technologies represent a significant leap forward, offering solutions that seem far more aligned with the realities of modern data processing and the demands of AI. As we look towards implementing these more widely, Professor, what are the persistent challenges that still require dedicated research and development? And conversely, what exciting opportunities do you see on the horizon to truly make these technologies widespread and effective in everyday healthcare?
The path forward is certainly exciting, yes, but there are definitely clear areas where we need to focus our efforts to realize the full potential. One persistent challenge, going back to the de-identification side, which still plays a role, is the need to significantly improve performance for those tricky, lower-performing PHI categories. We discuss things like locations, names, professions. They're often less formulaic, harder for models to identify consistently across different contexts.
So how can we improve that?
Several avenues are being actively explored. Integrating structured EHR data, where available, can be incredibly beneficial. Studies show it boosts recall, especially for names, by providing that verifiable context. Another promising direction involves using things like landmark names alongside contextualized embeddings, helping models understand location context better. And data augmentation techniques are showing great promise. Creating more training data, essentially. Yes, or better training data, supplementing training sets with data from other relevant data sets, or generating high-quality synthetic data using those LLM-in-the-loop methods we talked about. This has been shown to improve recall dramatically for difficult categories like names and IDs, boosting F1 scores significantly on some data sets. It's about giving the models more diverse examples to learn from.
What about the core NLP techniques themselves?
We also need to continue fine-tuning and expanding our approaches to word and character representation. RNN-based methods using word embeddings are still very promising for those broadly defined categories with high lexical variability where the same concept is expressed in many different ways. And character-level embeddings are proving useful too. They can significantly improve the recognition of abbreviations, common typos, and those tricky polysemous forms where one word has multiple meanings depending on context. Unit, meaning a hospital ward, versus a unit of measurement, for example.
Right.
Techniques like Chart2Vec have been shown to boost precision for location and date, though sometimes you might trade off a little recall. It's about finding the optimal blend of word and character level understanding for the specific task.
You mentioned a major open challenge earlier, domain transferring.
Ah yes, domain transferring. This remains perhaps the major hurdle. It refers to the difficulty in developing robust, truly off-the-shelf de-identification systems, or indeed many clinical AI systems, that perform equally well across diverse clinical domains, different hospitals, different countries, without needing extensive customization or retraining for each new environment.
But why is that so hard?
It's down to the inherent variability in clinical free text. You have local jargon, institution-specific abbreviations or identifiers, varying documentation styles and standards. A model trained meticulously on data from one hospital system might perform quite poorly when applied to notes from another, simply because the language dialect is different. It's like using a dictionary for one regional dialect in a completely different region.
And within that challenge, you mentioned annotation issues.
Yes, related to that are annotation ambiguities. Qualitative analyses have found that sometimes what looks like a model failure, a false negative, is actually due to differing annotation standards used when creating the original training or test data. One corpus might label something as PHI, another might not. This makes it really unclear sometimes whether performance drops are due to inherent model limitations or just inconsistent human labeling in the first place. There's a critical need for unified, ideally industry-wide, annotation guidelines to ensure consistency. Without that, properly benchmarking and comparing systems remains challenging.
And the data itself, is there enough diverse data?
That's another huge issue, the lack of diverse annotated data. Currently, almost all the main publicly available corpora used for de-identification research originate from just two major U.S. healthcare systems, Partners Healthcare and Beth Israel Deaconess Medical Center. This lack of diversity severely limits the generalizability of models trained on them. How well will they work in a UK hospital? Or a community clinic in rural Canada? We don't always know.
So what are the solutions there? More data sharing.
That's part of it. Exploring synthetic data generation is key. Distant supervision automatically generating weak labels from knowledge bases is another avenue. And crucially, we need to find ways to encourage the sharing of proprietary corpora, perhaps through secure methods like using pseudonymized embeddings rather than raw text, to unlock a wealth of real-world data diversity without directly compromising privacy. This data bottleneck is critical.
What about using data that isn't labeled?
Yes, utilizing unlabeled data offers significant opportunities, especially while fully labeled. Diverse data remains scarce. We can create anonymized word embeddings from large volumes of unlabeled clinical text to improve downstream tasks. We can customize off-the-shelf systems by fine-tuning them with domain-specific word embeddings derived from a target institution's unlabeled notes. We can also use techniques like generating pseudo-labels for large unlabeled data sets, which can then be used for training. And semi-supervised methods like active learning, where the model intelligently picks the most informative examples for a human to label, or self-training with just small amounts of labeled data, offer pathways to boost performance efficiently. Combining public data with smaller amounts of local data through domain adaptation is also effective.
And finally, combining different approaches.
Absolutely. The integration of available approaches offers a powerful opportunity. While those self-attention-based models, the transformers, are currently top-performing as standalone systems, studies consistently show that combining them intelligently with other techniques can push performance even higher. This could mean combining them with clever feature engineering, integrating rule-based methods for high-precision tasks, or using ensemble methods, essentially having multiple different models vote on the best outcome.
So the future might be hybrid.
It seems likely. The future probably lies in hybrid, modular frameworks that leverage the strengths of various techniques, rather than searching for a single silver bullet model. We urgently need the development of more open-source, extensible frameworks that actually facilitate this kind of integration and collaboration, allowing the community to build effectively on shared foundations.
Professor, that's an incredibly thorough look at the challenges, the nuances, and the genuinely exciting research opportunities ahead. It really paints a picture of a field that's both deeply complex and evolving at breakneck speed. But stepping back from the research lab for a moment, this is a real-world problem. It affects patients, clinicians, healthcare systems every single day. What is your call to action for the medical community, for healthcare professionals listening, for regulators right now? What steps should we all be taking?
My call to action is, I believe, urgent and really quite unequivocal. Regulations like HIPAA, while truly revolutionary for their time, are now undeniably outdated. Let's be frank about it. They were designed for a pre-AI, pre-cloud, pre-ubiquitous internet, pre-social media world. Regulators must, and I feel with a sense of extreme urgency, develop a new gold standard for patient data protection. This new standard must embrace these privacy-preserving technologies we've discussed. It must embrace zero-trust platforms where no entity inside or outside an organization is automatically trusted with data access.
So a fundamental shift in approach.
A fundamental shift. It's not simply about tweaking compliance checklists. It's about creating a robust, forward-looking framework that not only safeguards patient privacy far more effectively in our intensely data-driven world, but one that simultaneously accelerates vital medical innovation. We need to ensure that technological progress and individual privacy rights are not seen as competing priorities, but rather as complementary goals that actually reinforce each other. Unlocking new possibilities while actively building public trust is key.
And while we wait for regulators who often move slowly, what should industry leaders, clinicians, hospitals do now?
Critically, yes. While we absolutely must advocate for regulatory change, industry leaders, physicians on the front lines, healthcare executives making investment decisions, and patient advocates cannot afford to sit back and wait. The technology to protect patient data far more effectively while driving healthcare innovation already exists today. We've talked about it: confidential computing, secure federated learning, advanced anonymization techniques. Consider the current landscape. Developing and deploying a reliable, generalizable clinical AI algorithm often takes 2 to 3 years, costs maybe $3 to $5 million, and frequently results in systems with little inherent protection for the underlying data or the developed IP. We have the tools at our disposal right now to change that paradigm. It is, I believe, our collective responsibility to proactively adopt these state-of-the-art privacy-enhancing technologies. By taking the lead, by implementing confidential computing for secure analysis, using secure federated learning for collaborative model training, or adopting modern PETs, we can demonstrate that protecting patient privacy is not an obstacle to innovation. Instead, it is the critical pathway to enabling more ethical, more expedited, and truly transformative healthcare solutions for everyone. The imperative is clear. Act now. Leverage these advancements and build a healthcare future that's founded firmly on trust and security.
That's a powerful and truly vital call to action, Professor. You've brilliantly illuminated that critical balance between data utility and patient privacy, highlighted the inherent limitations and, yes, the growing obsolescence of traditional de-identification methods, and crucially, pointed us towards the transformative potential of these privacy-enhancing technologies. It really seems clear that the future of medical innovation hinges on embracing these new paradigms of data protection.
My pleasure. It's an ongoing conversation, but a vital one.
Absolutely. And for you, our listener, here's perhaps a final thought to mull over. Imagine a future where medical innovation isn't constantly hampered by privacy concerns, but is actually accelerated by deep, verifiable trust. How might this reshape patient care and research in your own specific field? And perhaps what steps might you champion within your own organization to contribute towards building that future? If you found this deep dive valuable, please do take a moment to rate and share it. It truly helps us bring more essential conversations like this one to the wider medical community. Thank you once again to our expert guest for his invaluable insights today.
Thank you for having me.
And we'll see you on the next deep dive.